Hello, folks. Okay, we are continuing a little discussion here with problem solving in chemistry, except this time around we are not talking about scientific notation. This time we are utilizing what's called significant figures to communicate uncertainty in a quantitative observation. Quantitative, this word quantitative basically means we're assigning a number to it. If we're making an observation of a mass or a volume or the length of something, we are going to communicate that by recording it, and we want to use significant figures to do that. Now, the idea here about significant figures is that nothing is really exact. There's always some uncertainty in every single measurement you can ever make. So if you take a picture and take a look at this picture here, this is what I do every day of my life. I'm making baby food for my son because I'm crazy. And I feel like if I would need it, he should need it. So anyway, I have containers just like this. And if you were to probably give a guess at how much is in these containers, like how much is pictured here, I mean, if it were me, I would probably say there's one full container and not quite a half of another. So maybe I'd say like 4 or 5 containers, 1.45. And you got to put a question mark there because you really have no clue. You could draw a line here and say, oh, well, about the halfway mark is there. So maybe it's actually 1.4 or 1.3. We don't know. This whole idea of significant figures is about the fact that there's uncertainty in every measurement. And this number we're guessing, it's important because if we were to say there's just one container of baby food, that would be totally wrong. And if we said there was 2, that would also be totally wrong. So we're making a guess at that tenths place, whether it's a half or a third or a fourth or a quarter, we don't know. But because it's our guess digit, we made a guess there. It is significant. That's what we're talking about with significant figures. So fundamentally, the rule with significant digits is that every single measurement has some uncertainty. That degree of uncertainty depends on how precise the device is. And so we take a look at that here. Precision has to do with repeatability, so every time you measure it would come out the same. When we're measuring things, you can see this ruler here has 2 different levels of precision. When we're saying it depends on how precise, up here we're just measuring in centimeters. And down here we can measure even smaller tick marks. These are probably millimeters. Okay, so that's what we're talking about when we're saying it depends on how precise the tool is that we're using to measure. And then when we finally make our measurement or report on it, you always report the digits you know for sure. For example, the 1 bottle of baby food, or in this case, a length of at least 2 centimeters. That's absolutely known, right? And then we always have 1 estimate digit. So in this case, we know that this piece of whatever that is definitely longer than 2. We have no idea how much. And down here, we know it's longer than 2, but we have a little bit of a better idea. So the measurement we would read on top would be 2, and then we have to make a guess. But, you know, we would have to make a really rough estimate guess. If we sort of made our own halfway line there, that would be 2.5. So I would guess this would be like 2.2 centimeters with a big question mark there. We don't know. And in the bottom, it's a little bit more straightforward. If we draw that line up, you could see it actually lands exactly on the 2.2. So those are actually 2 of the intended to be the same materials measured on 2 different, on 1 ruler with 2 different marks of precision. 1 is absolutely more certain, but both of these numbers, 2.2 in both measurements, are both significant. In this case, the more exact one is going to be the one that allowed us to go to millimeters with more certainty. Okay, so let's put a little star there. And we can continue to do this with a variety of different examples, and these are available in the course as an interactive. You can measure a whole bunch of different things on this same ruler, and actually this little guy here, he slides. he slides back and forth so that you can have a better idea. But in the case of this magnet, this is supposed to be a north-south magnet. I'll just draw my line. You can see how on the top where we actually have the tick marks, the edge of this actually comes to the very last tick mark. So I would say probably the measurement we read on top there would be 5.9 centimeters. And then on the bottom, you couldn't be so sure without all those tick marks. Right? It actually ends up that the measurement is the same. It's not going to be different on a different scale. But if you were to compare it, you just couldn't possibly know that. So maybe you would guess 5.8 or 5.9. And of course, the top one in this case is more exact because it has the extra level of precision of all those tick marks to help you determine exactly how long it is. And you can go on in the course and continue to make these measurements. The idea here being that you're always recording the exact number, and one estimate in both of those digits are going to be significant. So again, in the top measurement here, it looks like we're reading to about 9.2. On the bottom, however, you might guess it was actually just 9, but we would still guess a digit, so maybe 9.0. And of course, the top one again is more exact because it has those millimeter markings for us. Now, we aren't always making the measurements. In chemistry here, we aren't making any measurements, right? We're just doing a whole bunch of math and solving a whole bunch of problems. So sometimes we're reading scientific papers, we're calculating, or we're communicating, we're still using those measurements. So the word here is we may not always be making measurements, but we typically are using them. So we do need to know some rules with significant figures. The first of which is every non-zero digit is significant. Of course, that means every number 1 through 9. They're all significant. So we're going to ask you questions. What are the significant figures in this number? Or how many significant figures are in this number? Every number that is 1, 2, 3, 4, 5, 6, 7, 8, or 9 is significant. Any zeros between those numbers are significant. Zeros to the right of the decimal point, but with no non-zero digit to the right of them, are significant. For example, that would be like if we had the number 2.0 and it says there's no non-zero digit to the right of it, so it just ends there. It is significant. It tells us, as we said in one of those examples earlier, it would be a guess. It would be our estimate, so it would be significant in our measurement. And then finally, zeros that show order of magnitude of a number are not significant. So if we didn't convert something into scientific notation, for example, 1,000, 100, 2,500, 0.0025, and so on and so forth. The zeros that are not significant here are all of the ones that would show us how big the number is. Because what happens is we can actually rewrite these in scientific notation and not even show those zeros. We would show them as powers of 10. So in practicing or modeling these for you a little bit, I'm looking at how many significant figures there are in each of these examples. I'm referring to those rules while we do it. Test yourself here as we go through. In the first example, we have the number 50. And looking at the rules, it says all non-zero digits are significant. So if we just highlight every significant digit in all of these numbers, we're going to highlight every single non-zero digit, anything that is not a zero. So you can see in most of these examples, we have at least 2 significant figures. In the first one, only 1. Now we have to determine, and this is the tough thing with significant figures, is the 0 significant or not? So looking at the next rule, it says zeros between 2 non-zero digits are significant. So do we have any zeros between 1s and 9s or non-zero digits? Yes, we do. 501 has a 0 sandwiched in between these numbers. That means that all 3 of those numbers are indeed significant. This one as well, 501.0, that has at least 3 significant figures. We still have to evaluate this last 0 though. It's usually the zeros at the end and the zeros at the beginning that we're not always quite sure of. Actually, in these 2 situations, they happen to be examples of zeros that show magnitude. they show us how big that number is, 50 or 500. So the zeros that show magnitude are not significant. We know that because we can rewrite this as 5.0 times 10 to the 1 place. We don't even need to really include that 0 there. If we were to write 5.1 times 10 to the 2, we don't have to write any zeros at all. Okay, so significant figures in 50 is only 1, and those significant figures in 510, there are 2 of them. There are 3 in 501, and in 501.1, that's an example where we have zeros to the right of a decimal point, but there's nothing after it. So that is also significant. That's an example of a number with 4 significant digits. Looking at some more examples here, again going through and highlighting all of those numbers that are non-zero, knowing that they are always significant. Okay, and then looking at, so we did that, sort of, we can mark that off our list here. Zeros between 2 non-zero digits are significant. So this first number, 501.06, every single one of those is significant because the zeros are sandwiched between. So in total, we have 1, 2, 3, 4, and 5 digits that are significant. Also in the second number, 5,023.4, that 0 is between all the non-zero digits. So it's another 5 digits that are significant there. Now these are going to give us a little bit of trouble because there are zeros and we always have to evaluate whether or not they matter. We have a 0 at the end and it's not followed by anything, and that's this rule right here, zeros to the right of a decimal point but with no digit after it is significant, so that one's going to matter. But just like we had in this case where our tens and our thousands were not significant, we're going to have an issue here with zeros after the decimal point with nothing before them. They are never going to be significant. They're going to show placeholders and really how big that number is. So if we were to rewrite this in scientific notation, it would be 5 times 10 to the minus 2. And this other example would be 5.0 times 10 to the minus 2, because that 0 after the 5 is significant. So in 0.05 we have only 1 significant figure, and in 0.050 we have 2 significant figures. Oh my gosh, more examples. More examples. Going again through, all of our non-zero digits are significant. This is a good habit to get into. Even if you have a highlighter, it helps me. And so we mark that off our list first. Then we look at the zeros between those numbers. And we do have one in that second example, in the third example, in the fourth example, and the fifth example. So you can see that we know for sure we have 2 significant figures here, 3 here, 3 here, 4 here, and 5 here. Now we need to evaluate these zeros. We have zeros after the decimal point, but before the rest of the number. Those are going to tell us how big or how small the number is. They are never, ever, ever significant. Okay, so they don't matter. The numbers at the end always are, as long as there is no non-zero digit to the right of them. Okay, and they're after the decimal point. So we have a decimal point and a 0 at the end. Those are going to be significant. Okay. And this is tricky. It takes a lot of practice. So in the first example, we have 3 significant figures, also 3 significant figures in the second example, 4 in the next one, 5 in the next one, and 5 in the one after that. So you can see here in this case, where even though we have a whole extra digit in this number, it doesn't matter because it's not significant. It's just a placeholder. Now, if you're in the honors class, I was going to talk to you about adding and subtracting, multiplying and dividing. There are rules for governing those, but that's not something we're going to focus on a real lot going forward because we just don't have the time. So you did have some questions in your chemistry practice worksheet about this. You can go ahead and use the rules that I've outlined here for you, that when adding and subtracting, you the sum or difference has the smallest number of decimal places. And then for multiplying and dividing, the number of significant figures in your answer is equal to the number in the calculation with the fewest digits. This can become really hairy, so let's just ignore it for now. Hopefully this was